All right, like she said, I'm Bradley Davis, and I did some research on adaptive routing on contracted graphs. I want to talk a little bit about where my interest in this research came from, but first we need to talk about human drivers. Human drivers require a little bit of environmental information about roads, but not very much. They can compute routes by themselves, and they change navigational decisions at any moment. They have some intuition about which routes are typically fastest, and they know how they wish to handle a traffic jam. On the other hand, autonomous vehicles require massive amounts of environmental information about roads. They require routes computed by an external service. They have no onboard intuition about which routes are typically faster or how to handle a traffic jam. So after encountering a traffic jam, a human may wait it out, make a U-turn, take the next available exit, get mad, get out of the car, whatever. But an autonomous vehicle will just wait. That's not to say that an autonomous vehicle couldn't perform like a human, but we'd have to program it to do so. So that gave me an idea. Why not provide autonomous vehicles with regularly updated routes to their destination that make use of the wealth of information reported by all the other autonomous vehicles? Specifically, I'm talking about autonomous vehicles that receive route assignments from a central authority, like Google Maps. Each vehicle records the time it takes to drive along predefined segments of the road and reports those back to the central authority. The central authority takes those reports and updates its internal models. And at critical moments, the autonomous cars ask for new updated routes from the central service. So some of my research goals were to route vehicles so they avoid existing congestion, to reduce the mean travel time of all commuters, and to do the above in a manner that could be implemented in an actual routing service at the scale of a metropolitan area. But there's some inherent difficulties. It's all about speed. Fast route computations are just nice if you're trying to print off directions from Google Maps, but they're an absolute necessity, as you've seen in the last two presentations, if a car is going to make a critical decision based upon the result. Also, the graphs are very, very large. The San Francisco Bay Area graph is upward of 700,000 nodes and multiple millions of edges. Simplistic algorithms for finding the shortest path across such a large graph perform very, very badly. Let's take a look at the most simple shortest path algorithm that exists, and it's Dijkstra's algorithm. The implementation details are roughly covered up there, but what you really need to know is that you start at the start and you search outward in a circle. And that's a lot of wasted space. I mean, to travel across San Francisco, we had to look at every road in San Francisco. But all hope's not lost. Luckily, clever people have come up with ways to find the shortest path much more quickly. And there's a lot of them out there, A-star, transit node routing, and all that stuff. For my research, I focused on bidirectional Dijkstra's and adding shortcuts. Bidirectional Dijkstra's is simply starting a Dijkstra search at the start, stopping it, searching from the end, starting from the start again, and interleaving two Dijkstra searches until they intersect. The details are a bit more complex, but you can see the search space is like significantly smaller. Adding shortcuts is also helpful. You can exhaustively search the graph beforehand and find shortest paths between two nodes and add edges that represent those shortest paths. And the idea here is that if you have longer edges in general, then a Dijkstra search will reach a given destination faster and in a fewer number of hops. So I want to talk about contraction hierarchies. What is a contraction hierarchy? It's one of the newest methods for preprocessing a graph in order to improve query times. We're speaking about very large graphs. It involves creating a hierarchy of nodes, adding shortcuts, and using a derivative of bidirectional Dijkstra's algorithm. How do you build a contraction hierarchy? There's some rough pseudocode here, but the idea is that you sort every node in the graph any way you please. You take the smallest node and you look at all of his neighbors. And you try to find a path from any pair of neighbors that doesn't go through the node that you pulled out of the sort. If you can find one, you're fine. If you can't, you have to add an edge between the neighbors to represent the two edges in the node you pulled out. And then you continue pulling nodes out of the sort, but only inspecting the neighbors that are still in the sort. So you slowly reduce the amount of the graph that you're inspecting. This will be a little more clear when we talk about how we search a contracted graph. This is a very, very simple graph with 4 edges, and the node ordering is on the left, so lowest order to infinity. And it's already been ordered, and I've left out shortcuts just for simplicity. Let's try to find a route from blue to green. There's two conditions imposed on the bidirectional Dijkstra search. And that is that the forward search, or the blue search here, can only look at outbound edges that are higher in order, that end in a higher order. And the backward search, or the green search, can only look at inbound edges that begin at a higher order. And so you'll see that the two searches meet and we found the shortest path. But node ordering really, really matters. It can impact the contraction time and the routing time. And there's many different heuristics that are described in the original paper for sorting nodes, and they're very complicated. But one of the best is EDS5. So I want to tell you a little bit about EDS5. EDS5 has three main terms. The biggest one is the edge difference. And all that is when you look at a node, it's how many shortcuts do I have to add versus how many edges do I get to remove. So you want to contract the ones that remove the most edges first. And there's also a term for how many of my neighbors have been contracted, so that two nodes that are close together don't get contracted back to back. And the final term is the search space, which is a measure of how difficult it was to find an alternative path to replace the shortcut. Oh, and the 5 means that the search for alternative paths was limited to 5 hops to keep it quick. So I'm going to walk through a very, very naive node ordering. I'm going to choose to order these nodes from left to right, which is very random. So I'm going to take the first one and put it at 1, and the second one and put it at 2. And you'll notice when this one gets put at 2, there are no inbound edges with a higher order. Therefore, there's no pairs of neighbors, and there's no searching to be done, and no shortcuts to be added. And what that yields is something that looks suspiciously like we've done nothing. And, well, that's true, because searching from blue to green on this is just as bad as a regular Dijkstra search on a non-contracted graph. But we can do better. It's hard to explain the EDS5 in person, but we can just sort these nodes based on edge difference. And the idea here is that the middle 3 nodes have 2 edges that we can remove, and we'll be forced to introduce 1 shortcut because there are no alternative graphs in this line. So we pick one of them, and we set it at the lowest order, and we add the shortcut that represents the path. We do the same for the next one. And then the middle one, again, has 2 neighbors, and we'll add a shortcut. We do it again. The only thing different about this is that once that's contracted, these 2 shortcuts become upward neighbors and have to be evaluated for adding another shortcut. And the last 2 are trivial and involve no searches, and the result is this. So now if we search from blue to green, we only have to go 1 hop. That's it, and we have the path. And to spit out the path, we have to recursively unpack the original path. So the blue line has a pointer to the middle node. So you substitute the blue line for the 2 shortcuts, and for each shortcut, you substitute the 2 original edges, and you have your original path. The final product is something like this. This is a picture of a node ordering in white, and then after you add the shortcuts, it makes like a convex shape over the top, and that helps visualize the searching algorithm that basically always goes upwards and meets at the top of a hill somewhere. So the speed of contraction is a problem if I want to do adaptive routing. It can be slow. If you're only going to do it once, that's fine. But new traffic information means new edge weights, which means invalid shortcuts. And so the faster we can pre-process, which is in fact not pre-processing at all, the more sensitive and more adaptable our adaptive routing can be. So one way we can do that is by reducing the number of nodes and edges that go into the contraction process. And so road data is kind of littered with geometry information that's not important to making driving decisions, like where you're going to turn next. And so we can eliminate all of these edges that describe curves and other features that aren't important. And that leaves a graph with only straight lines, and that's all we need to produce a set of directions like you would print out online. The other thing we can do is use a different heuristic for ordering the nodes. It's kind of expensive in EDS5 to do a Dijkstra search for every pair of neighbors of a node. It compounds very quickly. And so I had an idea that's simple in principle and practice. If I just wanted to contract as fast as possible and see what happens, why not save the most work for last? And so N5 is a heuristic where you sort the nodes by how many neighbors they have above them. And that's it. You don't have to search for anything. You just keep track of that. It's a very easy thing to evaluate. And this is an example. So using N5, the blue node has a lower order than the green node. And that's purely because the green node has 4 upward neighbors. The blue node only has 2. So I wanted to run some experiments on larger graphs and see how it performed. It's important to note that the actual times for routing, while the trend is accurate, the implementation details can affect the actual number at the end. So this is a graph of the effects of node ordering on contraction time. And you'll notice that the red line represents what was described in the paper, EDS5 with a full graph with all the curves. And it takes quite a while to contract a graph about the size of the San Francisco Bay Area. But using N5, the purple and the white lines, the contraction is much faster. In fact, in later simulations, contracting all of the city of San Francisco took about 11 seconds on commodity hardware. And this is a huge improvement and very necessary. There are obvious trade-offs, and I wanted to see how bad they are. So this is a graph of the effects of node ordering on routing speed. Again, the red and the blue lines with EDS5 perform much better, but N5's routing speeds are roughly double at a graph size that's very, very large. And frankly, if you were doing this in a metropolitan area, the difference is quite negligible. And I think it's a fair trade-off for being able to update the edge weights every 15 seconds. There's not a lot I can say about this graph. This is just the number of shortcut edges that were added during the process. And really all this shows is that N5 as a heuristic produces almost as many shortcut edges as EDS5, which means it's not wasteful. It doesn't add wanton shortcut edges and anything like that. So what about the adaptive routing? Like, how do we use the information from the cars? Well, the premise is that we don't want to provide cars with alternative routes. That's something that currently happens a lot. We know what the shortest path is, but we're going to give you the second shortest or a different one just because we think something's wrong with the shortest one right now. We want to update the graphs frequently and recalculate the routes very, very often. And this provides increasingly accurate routes without the use of prediction. If you get a fresh route with like very new traffic data every time you hit an intersection, there's very little need to predict the future. So how do you turn traffic reports into edge weights? Again, I'm only collecting car A cross segment A and took 30 seconds. That's the kind of information I'm working with. There's no new traffic signals, no big networks of sensors or anything like that. So you collect the reports in bulk and you process them periodically about as fast as you can contract the graph. If there's a new report for an edge, you can use exponential smoothing. And this is a very simple model that could be replaced by something more complicated. But what I did is exponentially smooth it with a given factor. So if it were 50%, the new weight counts for 50%, and the old weight was, all the history of the old weight becomes 50%. And there's one more thing that's important. If we don't get any reports, we don't have any sensors to see what's happening on the road. So we have to assume that things are getting better. So we decay an edge weight in the absence of reports so that eventually another car will be routed along it and report back the conditions. Building test environments was kind of difficult, but OpenStreetMap provides lots of good data like classifications of roads, geographical coordinates, and stoplight locations. And you can use those to calculate distances, estimate free flow times from government manuals, and the most important is estimate the time to traverse any particular edge, which serves as the default weight. We also have to model vehicle behavior, and that's a very complex field, but I chose a simple cellular automata model where we divide the road into car length cells. And the general rule is a cell can only contain one car at a time. There's also a Nagel-Schreckenberg model that provides very strict rules on how vehicles can move. And it's basically a car following model where the car seeks to maintain a safe headway between the car in front of it while approaching a target speed. So I was going to run some experiments, and I'll show you the results of those. I just want to cover a few shortcomings. I didn't model roads with more than one lane. There's no passing available. The cars don't accelerate when they turn. There's no variation in vehicle length. They're all the same length. Left turns can be made into oncoming traffic, et cetera, et cetera. So does the model work? Does the car following model work? And I think this graph shows that it does. So this is just a distance versus time deal, and this is 1,000 cars traveling down the same lane. And you start to see that there's like these spasms where cars start to bunch together and slow down. You can see that happening, hopefully, a sec. Yeah. You can see that happening as cars just cram together and hit stoplights as they travel down the road. So then I ran the same simulation with with adaptive routing turned on. And what came out looks nothing short of chaotic. Could you imagine actually driving this way? This is why it's so suitable for autonomous vehicles. If you were driving and your phone told you to take these many turns and change directions this many times, you'd be so angry. But as crazy as it looks, the end result was a mean speed up of almost 1 minute. And that's a very short stretch of road with 3 stoplights on it. You can see here the mean, the normal curves of the durations of the times. And while, of course, some cars experience a slower routing time, the real takeaway is that you have a higher probability of getting a lower route time, travel time, rather. So I ran the same thing on all of San Francisco with 10,000 cars. And here's a heat map of the results. And they look pretty similar. One, because there's not really good resolution on the heat map. But you might notice, if you take a look at this road, and the non-adaptive, and over there, you'll notice that the adaptive increases the utilization of secondary roads. And that's a good thing, so long as that we don't flood the secondary roads and create more traffic. And just for fun, here's what that looked like. There we go. So you can see that even all these cars that started at random start and end points were routed with the service kind of congregate along major thoroughfares, which is a phenomenon you're probably familiar with in real life. You get directions from Google Maps, you'll likely be routed to a highway. But despite that, we're still able to improve the mean route time of these 10,000 cars by about 51 seconds. And so the last thing I did was rerun that same simulation, which I can't show you visually, but with 100,000 cars, and the results weren't as strong, but still an improvement of 12 or 13 seconds. That's all I have.